Waves and wave functions.
So wave functions are mathematical descriptions of the quantum state of an isolated quantum system. It corresponds to degrees of freedom of a maximal set of commuting observables. In 1887, Heinrich Hertz proved the existence of electromagnetic waves via a Ruhmkorff coil-driven spark gap and 1-meter wire pair as a radiator. In 1905, Einstein hypothesized the proportionality between the frequency f of a photon and its energy. In the 1920s, quantum mechanics was developed using calculus and linear algebra, which led to the development of wave mechanics. In 1926, Schrödinger published the famous Schrödinger equation, an equation based on classic conservation of energy using quantum operators, the solution of which is the wave function for the quantum system. In 1927, Pauli found a non-relativistic equation to describe particles and electromagnetic fields via a wave function using two complex numbers, now known as the Pauli equation. The movement of sound is simply air molecules moving in a wave pattern specific to each sound and is interpreted via vibrations in the human eardrum. Quantum particles and their states can be modeled via the Pauli equation, a multi-complex wave function. The transfer of energy from one substance to another moves in a sinusoidal wave. An oscillating system is an object that moves back and forth, repeatedly returning to its initial state after a period of time. At the equilibrium point, no net forces are acting on the object. All systems of which carry forms of vibration or wave motions are oscillating systems.
Natural frequency, or eigenfrequency, of an object is the frequency at which the system tends to oscillate in the absence of any driving or damping forces. This results in a fully closed energy system. If all parts of the system move sinusoidally with its natural frequency, then the motion pattern of the system oscillating is at its normal mode. Resonance is the phenomenon of amplification that occurs when the frequency of a periodically applied force is in harmonic proportion to a natural frequency of the system on which it acts. This causes said frequency to oscillate to a higher amplitude, increasing it throughout the system. In order to determine a resonant frequency, you take the natural frequency of an object and you find its inverse. An easier way to do this would simply be to put a microphone up to an object and a speaker and play a low tone and slowly increase the pitch.
Planck's formula is defined as E equals hc over lambda, where Planck's constant h is equal to 6.62, etc., times 10 to the negative 34 meters squared kilograms per second, while the energy constant c is equal to the speed of light squared, and lambda is the wavelength. Now, this applies to all forms of waves. However, waves have other properties, such as refraction, where it can be defined by its index of refraction, the actual refraction, the angle of refraction, or the angle of incidence. Now, the index of refraction for any form of wavelength is a constant, which can be defined by its angle of incidence over the angle of refraction. Please note this is important, because this will be on one of the extension questions.
The original idea for the project was debatably illegal, which, in my opinion, is a crying shame. But whatever, we moved on, and we eventually changed it to a bone conduction headset that would use resonant frequencies in order to implant sounds or voices into people's heads. It's the same concept as hearing aids, except it's a headset, meaning it doesn't intake external sounds, it's sounds that are programmed in. However, quarantine happened, so that went straight out the window. So we eventually changed it to finding the natural frequency of an object and using speakers to shatter it. But that will be for a later date.
Thank you for listening to this presentation and my rambling. And we both hope you have a pleasant day stuck in your houses because we have nowhere else to go thanks to quarantine. Have fun.